And we are live. Thank you everybody for attending the third CNC meetup for Switzerland for 2022. My name is Adrian. I am from Vision, the company behind the meetup, and today we are in the house of eBPF. So you can see here, for those watching online, there's an eBPF logo, if my finger points correctly. So we are in the house of the hottest technology of the moment, and this is really cool. Thank you so much, Isovalent, for hosting this event and providing the pizza tonight. I'm sorry for those watching online, there's no pizza for you. I'm sorry. The pizza is for the people right here. So that's a privilege, right? And tonight we have a very nice event. We are going to have Anders talking about open policy agents. We are going to have, where is he? So that's a privilege. Raphaël, he's over there from Isovalent. He's in the other room, probably preparing a few latest last-minute notes for his presentation. From Isovalent, he will talk about the eBPF, of course. And we have Simone and he's in the other room. I miss everybody. No, because they were outside. There we go. So we have Simone and his name I completely forgot. That's very sad of me. But that's how it goes. No, because they were and Scott, Simone and Scott, of course, from AWS. They are going to talk about Karpenter. We already mentioned where are the toilets. We already counted how many people are going to have pizza. So I'm not going to bother you anymore. Just one thing, the one public call we wanted to make. First of all, the goodies over there behind me, please take stickers and everything that you want, please. That's what it is for. And another thing that I wanted to ask, we are looking for a location for the CNC meetup of November. So if one of your companies, one of your employers would like to cooperate and to help this community to have the event, we already have the speakers. We are looking for a room in Zurich because we have speakers coming from abroad. Paris, Milano, and Basel. Basel is pretty much abroad, depending on how you look at it. Sorry for the people of Basel watching this, and I know that you're a lot, I guess. So, if you would like to contribute a room for this, we will be very happy. We are looking for that. So, there we go. Thank you so much. We have this is like, in auctions, and it's sold. There we go. It goes over there. Thank you so much. Now, a few more minutes to just get everything set up, and at 6:30, particularly for those watching online, because that's the program that we announced, so we would like to stick to it. We are going to start with Anders and his first presentation. A few more minutes to just so thank you so much for connecting, and thank you so much for coming. It's really, really cool. We are back in person, and that's really nice. Thank you. We are going to start with Anders and his first presentation. A few more minutes to just so thank you so much for connecting, and thank you so much for coming. It's really, really cool. We are back in person, and that's really nice. Thank you. We are going to start with Anders and his first presentation. A few more minutes to just so thank you so much for connecting, and thank you so much for coming. It's really, really cool. We are back in person, and that's really nice. Thank you. We are going to start with Anders and his first presentation. A few more minutes to just so thank you so much for connecting, and thank you so much for coming. It's really, really cool. We are back in person, and that's really nice. Thank you. We are going to start with Anders and his first presentation. A few more minutes to just so thank you so much for connecting, and thank you so much for coming. It's really, really cool. We are back in person, and that's really nice. Thank you. We are going to start with Anders and his first presentation. A few more minutes to just so thank you so much for connecting, and thank you so much for coming. It's really, really cool. We are back in person, and that's really nice. Thank you. We are going to start with Anders and his first presentation. A few more minutes to just so thank you so much for connecting, and thank you so much for coming. It's really, really cool. We are back in person, and that's really nice. Thank you. We are going to start with Anders and his first presentation. A few more minutes to just so thank you so much for connecting, and thank you so much for coming. It's really, really cool. We are back in person, and that's really nice.
All right. All right then. Hey everyone. Great to be here. I'm Anders, and for the next 40 minutes or so, I'll be talking about the Open Policy Agent project, or OPA. All right then. So again, hey everyone. I'm Anders. I work as a developer advocate at Styra, which is the company that created OPA, or the OPA project, and is still like the main core maintainer of the project. Again, I have a background in software development. I used to work primarily in identity systems, so a whole lot of OAuth, OpenID Connect, SCIM, so on. I have a background in software. Eventually, though, I got kind of interested. Like once we've established an identity, what do we do with that data? So we kind of solved the authentication part. In my previous roles, I got curious, like what is authorization? What is authorization? How do we solve that? And that's kind of how I kind of segued into OPA. So this is my third year working in the OPA project, or with the OPA project. My introduction to the project was in a large corporation where we had, I think we had development teams in 13 different countries using about as many different programming languages and about twice as many frameworks for web development and so on. So it was a very chaotic environment, or diverse. So, and we needed to solve, and it was in a regulated industry, so we needed a way to solve authorization, basically. And once we started looking into this, we kind of realized very quickly, like, there's no way we can implement authorization in 13 different programming languages by 13 different teams in 13 different countries, because all of these solutions are going to look different. And they're all going to come with a unique set of bugs and so on. And it's basically not going to be auditable at all. So that's how I found out about OPA, and we started working on that in that company. And I guess I had so much fun working on that project. So eventually I started working for Styra. So when I don't work on OPA, I enjoy cooking and food. So you might see football as well. And I'm from Stockholm, by the way. So the challenge, or the problem we're trying to solve here with OPA, it's really this. It's to try and manage policy. I talked about authorization, which is probably the most common kind of application for policy. But there's a whole lot of other types of policies as well. It could be basically anything. What type of cloud instances you can deploy, and so on. It could be what salary range should you be in based on your experiences, so on. So basically anything where you have a rule, or a set of rules, that's basically what a policy is. So what we want to do, we want to provide some way of managing policy in increasingly distributed, complex, heterogeneous systems. And of course, I mentioned like the application stack. It's probably the most heterogeneous of all our stacks. We have programming languages, frameworks, and so on. And in any larger corporation, you'll probably see most, or even all of these. So our applications will need to run somewhere, and we'll want to have rules governing that as well. What type of applications can be deployed in our systems, what type of security configurations can we have, and so on. And we want policy to apply to the actual hardware or cloud environments as well. And of course, we have data. We have tons of data, and we want some way to apply rules to those systems as well. So the goal of the OPA project is basically to unify policy enforcement across this whole wide stack. So that's a very brief introduction to OPA. And how does it do that then? It's an open source, general purpose policy engine. It kind of has to be general purpose in order to accommodate all these different technologies. And obviously, probably none of these technologies had OPA in mind when they were developed, so we're going to have to be very generic and general purpose. So it's a unified toolset and a framework for working with policy across the stack. We'll see some examples of that later. So a key concept in OPA is that you try and decouple policy from your business logic. So you can think of it a bit like how you decouple storage. You move that out from your application and into a database. OPA does kind of work in the same way, but for policy. So all these kind of if and else statements where you might say like if user is equal to admin, then do this or that. This is kind of the statements that you want to move out of your business logic and into a policy engine like OPA. So OPA it separates the actual policy decision from enforcement. So OPA makes decisions for you. You kind of ask OPA a question. So based on the policy you have here, should this user be allowed or not, or should we allow this deployment? But it doesn't actually do that enforcement for you. So OPA will serve a decision, provide you a decision, but it's up to you on how to act on that. That could be sending back a 403 response, maybe send a log line somewhere to an audit log, maybe contact the authorities, depending on the severity of the situation. The policies themselves, they're written in a declarative language called Rego. We'll look into that in a bit. Since it's a general purpose policy language, there's use cases pretty much on all of these technologies. But Kubernetes admission control is a popular one. Microservice or application authorization, infrastructure policies, data source filtering, CI/CD pipelines, pretty much whenever or wherever you might have rules, you can find OPA. Again, it's an open source project, a quite vibrant community, almost 300 contributors, over 75 integrations listed, kind of official integrations. I think we're up to 1,000 GitHub projects that are using OPA. Currently, 7,000 GitHub stars I checked yesterday, so this is a bit dated here. But yeah, 130 million downloads and so on. So it's a fairly big project and a fairly big ecosystem around it. But of course, OPA is not just some hobbyist open source project, but it's actually used in production by some of the largest corporations and organizations in the world. And if that's not enough to convince you, this is kind of my favorite quote here from Kelsey Hightower, saying the Open Policy Agent project is super dope. I finally have a framework that helps me translate written security policies into executable code for every layer of the stack. So that basically sums up all those things I said, but in a single sentence. So if that's what OPA is, how does it all work? There's a few key components to this. And the first one is this. It's the policy decision model. How can OPA work with all these technologies that had no notion or no, they did not have like OPA in mind when they built Kubernetes. They did not have OPA in mind when they built, I don't know, Postgres or what have you. So the way OPA works, it's basically this. You have a service, and we have a kind of broad definition of service. It's basically anything serving a request. So this could be a microservice. It could be the Kubernetes API server. It could be a Linux PAM module, or any of these other technology, a Kafka broker. So whenever a request kind of enters that service, rather than making a decision of its own, it rather reaches out to OPA, and it says, should we allow this or not? And that's a policy query. And that's basically just a JSON request, commonly sent over HTTP, but there are other ways to integrate OPA as well. So it sends some JSON data. This could be the path of the request, the request method, the user ID, or whatever data is relevant to make an informed decision. And OPA then, based on the policies it has in memory, and eventually, or optionally, some data, which could be anything relevant to make a decision, like permissions, or so on. So based on what it knows, it makes a decision, and it sends that back. And that response is also just JSON. So you have HTTP, and you have JSON. So any technology which can work with that, which is, of course, pretty much any technology in the last 20 years or so, can integrate OPA. And some of these products or projects make it easier than others. But you normally have, if you have something like an ability to inject a webhook or something like that. But if not, you can probably hack something in there anyway. So that is the decision model. As for deployment, I mentioned before that there's a few options. But OPA itself, it's a fairly lightweight binary. I think it's like 50 megabytes or something like that. So ideally, you deploy as many OPAs as close to your services as possible. So you don't have like one OPA server where everyone goes and asks for decisions, but rather each service has their own OPA with policy that is relevant to that service. So in a Kubernetes world, that would normally entail a sidecar container running in the same pod. So you query OPA on localhost, which is basically, or commonly, the latency of that is basically around a millisecond or so. So it's a fairly cheap operation. And this is the most common deployment model. But for some, if you're lucky enough to have a Go application, you can integrate OPA as a library. There's also plugins for Envoy and Istio-based applications, WebAssembly. There's a compile, a target, and so on. So there's a whole lot of ways that you can integrate OPA depending on your requirements. If you're unsure, you probably want the REST API. That's the easy option, let's say. So that's for deployment. The next key component, again, is the Rego policy language. It's a declarative. And of course, a declarative language means you don't really say how something should be done. You rather say what you want to be done. So it's a declarative high-level policy language, which is used by OPA. And just like a real-world policy, a Rego policy consists of a number of rules. That's basically what a policy is. And one of the kind of key goals of Rego is to try and mirror what a real-world policy would look like. So when you describe a rule to someone, that's basically what we want Rego to read like. So when you query a rule for a decision, that rule may commonly return true or false. For example, should this user be allowed to access this endpoint? Should this doctor be allowed to view the medical records of this patient, and so on? So we can say yes or no. That's the simplest of decisions. But again, we have any value that is valid JSON is also a valid decision. So we can be more granular, more detailed than that. If you want to, you might want to return a reason why someone was denied and present that to the user, and so on. There's a unit testing framework, so you can test your policies in isolation from your code. And again, I think like one of the benefits of decoupling policy is that, yeah, one, you can test your policies independently of your application, kind of decouple that from your application state, your application logic. But another main benefit of this is that your policy lifecycle is also decoupled from that of your applications. So if you need to add a role or you need to add some condition, you can update your policies and have that deployed without restarting or redeploying your applications, which is really nice when you work in these large kind of heterogeneous environments where you have hundreds or even thousands of services. So having to change an if-else statement somewhere in code and then having to redeploy all these services can be quite painful. It's a well-documented project, so check out the docs here. There's also a playground for you to try it out without even downloading OPA. So at this point, I'm think it's time for the demo. So I'm just going to show you some basic policy offering here. I don't know if this is big enough. Should I make it bigger? Maybe that's too big. Oh, OK, let's try that. So the first thing I'm going to do here, I'm just going to declare a package. I'm just going to call it policy in this case. It could be basically anything. It's more or less a module or a namespace or similar to what you'd find in other languages. And again, we said that any policy is a number of rules. And a rule in Rego looks something like that. We might have a rule which is called allow. And the anatomy of a rule is basically this. We have the rule name here. And we say that that rule is equal to something. In this case, we might say it's equal to true. And then it's followed by a body, which is all anything inside of these brackets. So if all the conditions inside of the brackets are true, or in the body is true, then we say that this evaluates to true. So it's basically a variable assignment, but it's a conditional variable assignment. That's basically what a rule is. So we're saying like, OK, so if the conditions in here are true, so if we say 1 is equal to 1, we know that to be true. So if we were to evaluate this rule now, we'd say Rego. And remember here, policy was the name of the package. Allow was the name of the rule. We can make that a little prettier here. Let's say. So if we evaluate that now, we'll see, of course, 1 is equal to 1. So no surprises there. If we were to do something like this, which is basically obviously not true, we'll see we got nothing back. So by default, if we a rule that does not evaluate is just undefined. So this might not be desirable. We might want to ensure that we always get something back. So we can say that by default, allow is going to be false. That's a pretty good baseline for security, right? So now if we evaluate this again, we'll see now we're getting false back. So now we at least have, we know that we're always going to get something back. Of course, in a real scenario, comparing two constants isn't really useful. So what we normally want to do is we want to use some of that data that was provided by the caller. And Rego has two global variables. One of them is input. And the kind of notation for getting data out of the input is similar to anything else which is JSON-based. So you could say input user roles or input user ID is equal to Anders. And now this rule is going to check anything coming in with the input, check is there an attribute called user, does that have an ID, and is that equal to Anders. So what we're going to have to do now, so we're going to create a little JSON file here just to simulate. So we had a user, and we had an ID. So this is what a request might look like then. Normally you'd send this over the REST API, but it's all just JSON. You just provide some data. Realistically, you might have something like a request. You say method is equal to get, and some path components here could be users, Anders. Oh, okay. But the first policy we have here is just let's change this to admin and make it more real. So that makes sense. An admin should probably be allowed to do whatever it wants to. So we're going to try this policy again, but we're going to add the input file there. So we're going to see we're not allowed because I think we don't have the admin ID there. So we're going to change that. You're going to see like, okay, now we're good. So unless we're admin, we're not allowed. We might, for example, so this is a very simple rule, and we only have one condition here, but we can add as many of these as we want. And the logic for inside of rule bodies is that these conditions are ANDed together. So all of the conditions need to be true in order for the rule to evaluate. So if we want to add another rule with other conditions, we can simply just do that. We say allow is equal to true. And if we add another rule with the same name, these rules are going to be ORed together. So if one of them is true, the decision or the outcome is going to be true. So we might want to say that if input request method is equal to get, and the input request path, and that was an array. So if the first component there is equal to public, oh, typo. So if someone is doing a request at the public endpoint, we should allow that as well. And in this case, we don't even care what the ID of the user is. So if we were to change change this back to Anders, and we're going to see. And we're just going to change the path here. We can see that we're allowed on that conditions as well. So this is basically a very simple demo, kind of showing how you start and build these conditions or rules, which together build up your policy. And these are all just simple like comparison examples. There's a whole lot more to Rego and OPA. I think there's about 170 built-in functions. So anything for doing like checking strings, working with arrays, sets, and so on. You can even do like network calls and things like that from your policy. So, but the basics, if you know this, you know the most important bits of OPA. This is basically kind of the foundation of how it works. So if all the conditions are true, the rule evaluates to true. And again, we wouldn't need to say it's true. We could say yes or no, or return an array, or maybe return some obligations. Any valid JSON value is a valid decision. Okay, so that was a quick demo of OPA and Rego. Before I proceed, any questions on that?
Is the kind of return value of a rule type checked? So can I return a string in one or branch of a rule and a boolean in the other? Or?
Yeah. Okay, yeah. So the question was, can you return like a string for one allow condition and a boolean for another? No, you'd need to have another rule to do that. So you can't have different types returned for the same kind of rule. Because yeah, essentially I think you could do some pretty weird things like having one decision say deny and another say allow, and try and have them both returned. Okay, so since this is a CNCF meetup, I know there's a few people interested in Kubernetes. So Kubernetes admission control, it's another popular use case for OPA. And yeah, this might be very old news for the audience, I'm not sure. But the way the Kubernetes API works is basically this. Before anything is stored in the database of Kubernetes, which is of course etcd, it has to pass a series of modules. So when you type in kubectl apply my file app.yaml, that request is first authenticated, it needs to be authorized, and then it passes the admission controllers, where there's a mutating one, which can modify the request before persisting it, and there's a validating step where we can say that I have some rules here, and unless those are fulfilled, I don't want this. I don't want to allow this to be persisted. So these modules are chainable. You can have as many admission controllers or authorizers as you wish. And there's, of course, a bunch of built-in modules, which comes with Kubernetes. For authorization, of course, RBAC would be the most popular one. But for our use cases, this is really what we're interested in. It's the webhook one. And we don't really do authentication, but for authorization or admission control, OPA is kind of a perfect candidate. Again, it's JSON over HTTP. That's basically what we do. So OPA just fits right in. And I'm gonna, I kind of zoomed in here on the validating one. And the reason I did that is because it's by far the most popular module to extend. And the reason that is, I'd say, is because it allows us to build these kind of guardrails around our clusters, where we can say things like no deployment should be allowed unless all the containers here are, or the images for these containers are fetched from our internal Docker registry. Which could be for security reasons or just like organizational things. Labels, so organizational rules. You might want to say like no resource can be deployed unless it has a label that clearly points out the owner of this resource. Label, annotation, or it could be a cost center, a team, or what have you. Ingress or host path uniqueness, and this is an interesting case where because you need to look not just on the incoming resource, but also on all the data that actually is currently deployed. So if you were to deploy an ingress and the host name for that ingress, or the host of that ingress, or the path is already in use, if you deploy that, you're gonna basically overwrite what's already there, which could, of course, be disastrous. Ensuring TLS for services, denying insecure attributes, like the host path volume mounts. You might want to put limits on your resource allocations, pod security policies, but basically anything. So anything you can think of. If there's any rule you want to enforce, OPA is the right tool for that. So I don't know if this is really clear here, but so the principle should be familiar by now. You have JSON in the input. So in this case, our client is the Kubernetes API server. When you say kubectl apply, the API server sends a request to OPA. It says, can we allow this or not? In this case, we just have a very simple rule where we say, if there's not an input request object metadata label cost center, we're going to deny that. And we're going to, in this case, we're going to return a string where we say every resource must have a cost center label. So we give the user or the administrator a chance to know, okay, of course, I need to add that label. They can correct their mistake and redeploy. And the output, of course, is that warning to the right. So the principle is the same, whether you work with authorization for applications, admission control, infrastructure policies, CI/CD pipeline policies. So if you kind of learn the basics of OPA, you have a wide array of technologies to apply policy to. So authorization, and authorization is such a big topic. I'm not going to cover it here. I just figured it might be interesting to see kind of a map similar to what we saw for the Kubernetes API server. In this case, this map is, of course, a bit more complex. Authorization is, and in particular, distributed authorization is complex. So a modern kind of distributed microservice environment where you want to do authorization, and you want to do that according to the zero trust security model, which basically means you don't make assumptions in one service that this request over here, it's already passed these other two, and they did authorization, so I don't really need to do that. You don't make those kind of assumptions. So authorization is basically performed in all services. So you have an identity system, which commonly returns something like a JSON web token or something to assert the identity of the user. And with that token, you send a request across these services, and they all do authorization. And the distributed model here, it basically means that we don't want the services to reach out to some external component at policy evaluation time, because that's going to be expensive. The OPAs are running, again, as sidecars. So they are essentially running on localhost. So for a request like that, OPA might add 5 milliseconds to the total request time, which is commonly, I'd say, within our latency budget. If it isn't, we have other options available too. But reaching out to an external service, that might be 10, 20 milliseconds. And then we'd be talking about like 50 or 100 milliseconds just to do authorization. And that's just involving 5 services. Like in most systems, you might have 10 or 20 services involved to service a single request. And then we might be up in like half a second or so. So that's not really a viable model. So the way policies and data is distributed is asynchronously. And from a control plane, and when I say a control plane, that could basically be an S3 bucket. It doesn't have to be something advanced, but just something where OPA periodically goes and fetches policy and data updates. But it doesn't do that at policy evaluation time. It stores a copy of policy and data in its own memory. So the decisions should be very fast. Okay, so that's basically OPA for a few use cases. How many of you have used OPA in the past? Okay, that's great. So the next section here is going to be for you. So some new features of the project. There's the feature called Delta bundles. I mentioned that OPA periodically goes and fetches data and policy. And it's been up until now, that's been a pretty simple process. Where if there's new data, if it's not like a 304 response from the server, OPA goes and fetches all that data. But of course, if you have gigabytes of data, it's not economical to go and fetch all that data with every update. So now we can distribute only the deltas or the diffs of what actually changed. So it requires more logic server side. You can't just have a dumb S3 bucket or Nginx. You need something to kind of calculate the delta and serve that. But provided that you have that, that's a new thing you can do. There's a strict mode for OPA, so kind of catching a lot of simple mistakes to make or unused variables and so on. Metadata annotations, you can annotate your rules or your policies, just as you can see in many other languages, and then you can query for that metadata as well, or you can use it to build docs and so on. OCI bundle registry support. So I mentioned like S3 buckets, Nginx, and so on. Now you can also distribute your policies over OCI bundles. There's disk storage. OPA normally kind of carries everything it knows in memory, but for if you have like hundreds of microservices and you have a lot of data, it all adds up. So disk storage is another option if you have a lot of data. Function mocking for the unit test framework. New built-ins for supporting GraphQL, which has been like a very common request. There's named built-in function arguments. This is more of an internal detail, really. But for tooling like the VS Code plugin for OPA, where you can get like autocomplete and pop-ups and so on. So that's a few of the new features in OPA, and a few things that are currently on the roadmap. It's the big thing is dependency management. It's basically the way it works today is basically that you assemble a bundle of data and policy, and you can pull in whatever you need when you build that bundle. But there's not much in terms of helping you do that. What we'd really want here is just to say, like, my policy depends on this kind of utility library or this these helper policies and so on, and OPA would just go and fetch that when you build the bundle. Better output when you have test failures. You actually show the diff. That's something we're working on as well. Non-deterministic values and decision logs. So by default, and like 99% of all policies in OPA are deterministic. It's one thing that we really want. It's a thing and it's one thing that sets OPA apart from, like, why can't I just use Python or any other programming language? One thing we really want is to ensure that provided you have some input data, you will always get the same kind of response. So we want OPA to be deterministic, but for the few things where there is some randomness or some non-deterministic things, we still want to be able to log those things so we can replay decisions later, because that's basically what the auditors are going to ask when they come knocking on our door. They're going to say, how come this user was allowed access to this or that system? And we want to be able to kind of replay what happened 3 months later. Yeah, and there's a bunch of smaller things like optimization flags for tooling, rule tracing, schema validation, more operators and so on. If there's interest, I'd be happy to answer or talk more about those later. Yep.
And schema validation, is it about asserting that the input I get to the rule matches my expectations?
Yes, yes.
Great.
So it's basically what you do today in policy. You'd say, like, but rather than having to do that kind of what is it called, like plumbing, or it's basically just checking for, is this attribute available? Rather than having to write that in your policy, you can just know that this has already been checked. So you can just kind of focus on what actually matters and not having to do like type checks or so. All right, so if you're interested in OPA, here's my advice for getting started. I'd suggest you start small, kind of like we did in the demo there. Just try it out, write a few simple policies and rules, evaluate them, see what happens when you change something here and there. And of course, the unit test framework is also a great tool for learning. The OPA docs, good resource. Browse like the docs on the built-ins, the basics, and so on. And yeah, once you kind of pass that stage, I'd suggest looking at some applications that you've worked with in the past or something that's near to you. And again, when you do that, you can start small as well. You don't need to rewrite your monolith app to use OPA from day one. You can start with a single endpoint maybe, or maybe a single user, a single role, or so on, and delegate some of that responsibilities to OPA. See how it works out. Things like decision logging, all these management capabilities, setting up a bundle server and so on to truly kind of decouple policy from your application. And yeah, the Styra DAS, it's Styra's offering for that. It's a control plane for OPA, and there's a free edition, so you can try that out. Styra Academy is another learning resource for OPA and Rego. And of course, there's the OPA Slack community where I think we're 6,000 people or so. So any questions?
We can probably take one question.
Yeah, one question. So make it a good one.
I have one question. I don't know if it's a good one. When you mentioned that you don't have a single server,
where you call OPA that you have this concept of the sidecars. So when you update the rule set, how does that work to make sure that all the sidecars have the newest information? How does that get deployed?
Right. So OPA commonly works with a pool-based approach. So you start OPA with a configuration file where you say, my policies and my data is over there. And go and fetch it every 10 seconds or every 2 minutes or so on. So you'd configure all these OPAs, and you can configure as many remote endpoints as you'd want. So you can also ensure that only the policy and data which is relevant to that service is getting pulled out.
We are going to have time for questions afterwards at the end. Right now we have to, unfortunately, well, unfortunately, but the time is up. Thank you so much.
Thank you very much.
All right. Well, hello, everyone. So my name is Raphaël Pinson. I'm a solutions architect. I work here at Isovalent. I'm not very often in this building because I work from the other side of Switzerland. And I work on Cilium, Hubble, and Tetragon, so products that are in the CNCF and integrate with cloud-native applications. And today we're going to talk specifically about Tetragon, which is the latest open source product that we have in the Cilium family. So first I'm going to talk about why we need Tetragon and what it does, talk about security observability, runtime enforcement, and then if we have time, hopefully questions. So first, Tetragon, I have this beautiful t-shirt, thanks to my colleagues in the US who made this. What is it? It's a security observability and runtime enforcement tool that is part of the Cilium family that is within the CNCF. So it's an open source tool that is currently within the CNCF projects. Right? And what does Tetragon do? It allows to observe security events on machines using eBPF and even to enforce rules on these events. It can allow to do a lot of different things, from observing data access, network flows, namespace escapes and privilege escalations, file access, lots of different things around syscall, even eventually accessing the function calls, the code exec. And why can it do all this? Because with eBPF, we're plugging directly at the kernel level, and we can see everything that's happening on the machine. And then based on this, we have different types of structures that we can use to collect these events and either provide observability on these events or even react to these events to prevent execution, for example. And then we can extract this information from the kernel, and there's an agent running in user space that allows to gather this information and send it to, well, you name it, Grafana, Prometheus, some kind of SIEM, could be Elasticsearch, could be an OpenTelemetry format, or just JSON events. So let's dive into this and see how this works and why we need this kind of tool. So we're talking about runtime security, and in particular, security in real time here. We have some machines running. It could be running Kubernetes. It could be actually something else, running with a kernel, with a Linux kernel in particular at this point. And we want an active protection for the workload that's running on these machines. So 3 things we'd like to do. First, detecting malicious activity in real time. We'd like to report this malicious activity if we find it using observability, some form of observability. And even better, we'd like to prevent this malicious activity if possible. So when it happens, when it's happening, block it, prevent it from happening. So there's different ways of doing this. We'll see about this. So what activity do we care about first? Could be network traffic. We want to detect some malicious network activity. It could be file and I/O activity, reading, writing files, anything that has to do with input-output on the machine. It could be running executables. Someone is trying to, I don't know, mine Bitcoins on your machine, and you want to detect this, for example. Didn't happen to anyone, right? It could be some system call activity that shouldn't happen. It could be any kind of privilege escalation, from changing namespaces to abusing, sorry? Yeah, I'm trying to be careful. Abusing capabilities, typically in container capabilities, for example, and so on. So how can we spot this activity? There's been tools that have existed for many, many years, actually, that have been used for this. LD preload, ptrace, seccomp, LSM, and then finally eBPF. So I'm going to go a bit through all of these and see why they're good, why they're not good, or not sufficient. So LD preload is probably the oldest way of doing this. And the whole idea of LD preload is when you have dynamically linked binaries, these binaries don't have the syscalls in themselves. In the binary, they make calls to the system, and they rely on a standard library in your OS. And this standard library will be the link with how to call the kernel to make tasks executed by the kernel. And what LD preload does is that it will allow you to replace the standard library with your own version of the standard library that will essentially work as a proxy between your application and the kernel. And so it will catch the syscalls made by your application to the kernel and replace them with pretty much whatever you want. And because this is a proxy, you can have visibility and you can actually replace whatever your application is trying to do. This works. It's been used for many years. There's a few problems with this. First, you need to inject it for every application if you want observability. So an application that doesn't have this LD preload will not be observable. And second, you can easily escape this by using statically linked executables that won't use the standard library. And this is very common in the cloud native, especially Kubernetes environment, where you have containers with statically linked binaries. So this is no good in our context. The second way of doing this is trying to catch the syscalls when they're being made to the kernel. This is what ptrace does, or sepconf, or even you can use eBPF with kprobes for this. The problem with this approach is that it is prone to an issue that is the time of check versus time of use. So time of check versus time of use talked out with syscalls is the fact that your application will prepare a call to the kernel, will load the parameters. This is when you will observe what's happening. But then when the call is actually made, the parameters can be changed. So you can have a call to modify a file that is perfectly fine for you. And then when the call is made, right in between the check and the call, you can actually change the file that's being written, for example, and write to a file that you're not supposed to write to. And this is problematic. There's some papers that have been written that you can access on this. And so this is not reliable enough for what we're trying to do. So we need to make the check at the right time. That is not when the syscall is actually prepared, but when the parameters are already sent to the kernel and are being executed, because we know that these parameters are actually the ones that are being used. So how do we do this? Fortunately, there are some solutions that already exist. One of them is actually used by very common security approaches, which is AppArmor and SELinux, which rely on LSM, Linux Security Modules. And this allows to actually catch the syscall when it's being applied to the kernel. It has a stable interface. There's some things you can do that are very well known in there. It's a safe place to make the checks. The problem is essentially, sorry, I'm going to get back to this. The problem essentially with this is that first it relies on a module. And adding modules to Linux usually adds instability. It's another part of the kernel in a way that gets executed in the kernel space without specific verification, and that adds some attack vectors to the kernel. So that's the main issue. And the second issue is that the LSM API itself is quite limited, so you can't do everything you'd like to do as far as checks. So here I'd like to introduce eBPF and maybe do a little primer on eBPF, because you might not be familiar with eBPF. It's been around for quite a few years, and more products are using it. At Isovalent, we use it pretty much in all our products. That's like what we do at Isovalent, is implement stuff with eBPF. So what is eBPF? eBPF is a system within the Linux kernel that allows to modify the way the Linux kernel works, kind of like a Linux kernel module, if you will. Except you inject small programs that are written usually in a subset of C that get compiled into an assembly language and into bytecode, essentially eBPF bytecode. And this is very restrictive. You cannot do whatever you want. So when you inject this bytecode into the kernel, the eBPF system and the kernel will verify the code. It will run every possible path that this code could take to verify that it will terminate, that it won't cause any issues to the kernel in terms of security or in terms of crashing the machine. And then if it allows this BPF code to be injected, then only it will compile it, make it into machine code so that it gets executed at the same performance level as the kernel. So this allows to observe things, and it allows to act on kernel actions as well. Because what happens is that when a process makes a call to the kernel, typically a syscall, here to execute a program, for example, normally this syscall would go directly into the scheduler. With eBPF, which is standard in the Linux kernel and now coming into other operating systems as well, what happens is that you can actually catch this syscall and act on it. You can record what's happening, but you can actually block it even before it gets executed, which is very interesting compared to the other approaches where you see it coming, but by the time you react, it's already been executed. So this is an example of observability, by the way. Usually the programs are very simple in terms of size. There's an amount of complexity you can inject for security reasons, but it might be a little bit complex to program. And BPF programmers, I'm not one, BPF programmers like to say that, apparently they like to say, that one of the toughest things in their job is to convince the kernel that they're not trying to harm the machine, because the verification is quite strict. So eBPF is actually a technology in the kernel that is backed up by several companies. These are the founding members of the foundation. So one approach instead of LSM first is to use BPF LSM. So you use the LSM interface that is still, it's good, it's known, it's well known, but instead of implementing it with a Linux kernel module, you implement it with eBPF programs, which gives you more reactivity, you're closer to the kernel, and less vector attacks possibly because your programs, your BPF programs are being very strictly verified by the kernel before they're used. So this is one possibility. Unfortunately, this relies on Linux kernel versus 5.7 plus, and a lot of images or a lot of OSs that you find at the moment do not have kernel 5.7 plus. So this is not an option for many people running in production. So enter Tetragon, and the idea with Tetragon is how about we use eBPF because it gives us visibility into the kernel, it gives us the possibility of actually blocking syscalls in the kernel if we need to, and actually instead of the LSM API, which is good, which is stable, but is quite restricted, we're going to use some more or less stable API in the kernel. There's some calls that are not per se very stable, to open files, to manipulate networks, and so on, but are stable enough that we can actually rely on this. And thankfully, newer versions of the kernel, we actually get mappings for these functions that give us stability. So we're going to use kernel knowledge to hook into sufficiently stable functions in the kernel to handle this thing in a dynamic way. And one thing that is great with eBPF is that we can have multiple eBPF programs watching different parts of the kernel, and they can communicate with each other using structures, using maps, in such a way that you can correlate events even for the actions. So if you have things happening on the network and on files, you can correlate these events and have reactions that match this. And you can even filter the events in the kernel because eBPF allows for enough logic to be running in the kernel and filter the events before they're extracted from the kernel. So what do we have here with Tetragon? What we have is we have deep visibility because we can see pretty much everything that happens on the machine go through the kernel. So we can see this. We can see what happens in the system. We can see network. We can see different protocols because we could parse these protocols. If there's an HTTP flow that is going through the kernel, we can actually parse it and see the HTTP request. Same for DNS, same for anything else, potentially. File system activity, applications, it's totally transparent. We don't need to code anything in the application because we're at the kernel level. So it's going to go through a kernel anyway. The application doesn't need to know what's happening. It doesn't matter which language you use for your application or how you compile it. It will go through the kernel at some point. It's very low overhead. We are not running this logic. The watching logic is not outside of the kernel. It runs in the kernel. And the thing is that the kernel is by itself already an event-driven interface. It's not something the kernel in your machine doesn't do things on its own. It just reacts to events from the outside. And this is great because we need to react to the same events. So we're just looping into the event logic of the kernel, and it adds very little overhead. On top of this, a lot of the performance overhead that we get usually stems from the communication between extracting the stuff, the data from the kernel, and getting it into user space for visibility or for treatment. And this is due to the fact that there's a lot of events. You can imagine if you're watching sockets, you're watching network flows, a lot of things are happening. If you're extracting this from the kernel, that's a lot of things that you're extracting. But with eBPF, what we can do is that we can already aggregate all this stuff in a logical way and export just what we need to export. So there's less traffic here between what's running in the kernel, which is event-driven, and the logic that we have in user space, which is essentially sending it to Prometheus or reacting to it in some way. Right? So plus we can get all this logic here in eBPF, the different structures that allows to pretty much allow the BPF programs to communicate with each other for event correlation. And there's lots of integrations we can do with this, because once the events are exported, we can export to Prometheus, to Grafana, to different types of SIEMs, FluentD, OpenTelemetry, Elasticsearch, and so on and so forth. And this is done in user space. Context is everything. If you get an attack, if there's a security breach on your system, having a log, having an alert on something is not enough to understand what's happening. If you have several events, you have to be able to correlate these events to understand really what's happening on your system. So the contextual information is very important. So with Tetragon, we can observe everything. So these are some examples of the things we can get here in Grafana. We can get network interface metrics. We can watch all the interfaces. And you see here that we see by machine, typically in a cluster, and by interface, so the Cilium host, the Docker 0, local host, ENS5, and so on. And we can see the amount of traffic that is going through each interface because we're just observing it in the kernel. We can even see the latency, and this latency can be correlated by DNS name, for example. We're able to see the DNS names because we see everything going through. So we can see here the latency by service that is called. We can look for traffic by pod, for example, by source pod, because we have access to the metadata that is either, in the case of containers, in the C groups, or in the case of Kubernetes, we can have access to the Kubernetes metadata. So we can correlate the traffic with the pod names and know that this pod is actually the one using most traffic, generating most traffic. We can have TLS or SSL visibility because we're able to see all the traffic with TLS. We can see TLS versions. We can see how much traffic is used with TLS to specific SNI names. We can see the TLS handshakes that are made by pod or to specific destinations. So we have a great visibility on the system at a very low level. And here I'm talking about Kubernetes and specifically, but this could be done even outside of Kubernetes on any machine with a Linux kernel with eBPF, which means pretty much any machine that is up to date. Here are some examples. We've exported our data to Splunk. This is an example of a Splunk request where we're looking specifically for TLS version 11010 and getting all the information. And this will give us a table with all the different TLS communication that has been seen in the kernel of the machine. And we can see the source namespace, the source pod, the source image, and so on, so we can get information on which pods are actually using these versions of TLS and which binaries are being executed, and so on, which can be very useful for a blue team, for example, in this case. We can observe protocols, DNS, HTTP, TCP, by parsing this in the kernel. This is an example of our command line interface, the Tetragon interface that internally we call Amazing CLI, because it makes like nice colors. We don't see colors here, and nice emojis. And this is an example of a curl being executed anywhere on the machine. Could be in a container, it could be anywhere on the machine. And we see the curl command being executed, so the process is starting, first event, all the DNS events for the resolution. So we see it's in a container, and this calls to kubedns to get the resolution. Eventually, we get an IP, so we see the IP being returned. And then we see actually the TCP traffic, how many bytes were exchanged, and so on. We can audit listening ports. Again, from this data, we can see which ports are being used. And we see in this specific pod with these labels that there's actually 2 ports being opened for listening with 2 processes attached. One is Python, one is NC. And NC has a parent process of bin ash. So probably someone is logged in, has executed a shell in that container, and has launched an NC. This is looking a little bit funny. We should look into this. We can detect DNS bypass attempts, for example. Here, we're looking for flows that target UDP port 53 that is in the reserved world identity in the case of Cilium, and we see that it targets an IP that is external to the cluster, which shouldn't happen in a Kubernetes cluster. Can detect Nmap scans. We can monitor execution in syscall. So this is an example of an event as we can have it from Tetragon. This is what you get from Tetragon. You get a list of events like this in JSON. You can export them, do whatever you want with them. And you see that this is a process exec event, so a very basic event when a process gets executed. We get the exec ID, we get the PID of the process, the UID, this is executed by root, in which directory was executed, the binary that was executed with the arguments, the flags, the start time. If it was executed in a pod, you get information on the pod, the container, the namespace, all this that was gotten from Kubernetes. The Docker information that was executed in Docker in this case, and so on. And then you can correlate these events yourself or rely on a correlation engine. Plus, you can add your own events. This is an example here using a Kubernetes CRD that is called tracing policy that we ship with Tetragon. In this case, I would like to monitor mounts whenever there's a mount that is executed, a directory that is being mounted anywhere on my system. And so I know the name of the syscall, and I know the arguments that are being passed. We have examples of this, and I want to monitor this. So just adding this to my Kubernetes cluster, I will have new events popping up for the sys mounts, and then I can correlate them myself. So we have a collection, depending on the open source version or enterprise versions, we have collections of tracing policies by default. And then eventually, and this is an example in Isovalent Cilium Enterprise that uses Tetragon as part of the enterprise solution. We have an interface here that correlates the process execution with the network flows. So you can see here that there was a pod called crawler 690 and so on that was executed in the tenant's job namespace on a Minikube Kubernetes cluster. We see what was executed before the process started. This is pretty interesting. The stuff you never see actually, usually when a pod is starting. And then the pod starts here. You see containerd starting it. You see kubeproxy, containerd shim, and then eventually there's our pod starting here, node server.js. That's the container starting. And this server.js makes several connections to this IP, to Elasticsearch, to twitter.com. And then we see here 5 minutes later, it says 5 minutes. 5 minutes later, we get an NC connection to a something.notreverseshell.com that makes a call here. And so, you look at this and you're like, okay, there's been some breach in the Node.js application, and someone has managed to start not so reverse shell apparently, but something that is not right? And you can correlate this in this UI here and see what happened actually in your pod. So this is the kind of request that you can do as well in Splunk to reproduce this to see late process execution in a pod. You can monitor file access. So here we're looking at some specific files, etc password, opt app, etc shadow, and you can see which processes are accessing it, potentially which pod, which source image, what is the shell that is the most used to access them, and so on. And this gives you an idea of where your vulnerabilities might be. And this is more on the Cilium side, actually, but it's still the same logic where we're analyzing flows, where here we can see network policy compliance. So here we can list all the flows that are being observed in the kernel and see all the flows we see here are being forwarded, and we can see if there was a policy that had been applied. And if you find flows where no policy applied, then you can think, hey, maybe I'm not actually doing this right. Maybe I'm missing policies. Even if the flow is allowed, there should be a policy applying to it to allow it specifically, right? If nothing is applying, maybe I'm not doing the zero trust thing seriously. You can parse HTTP and gRPC. So here we're seeing actually a cross-script attempt here that can be analyzed through the the parsing of this HTTP request. And then finally, the runtime enforcement, which is the most exciting thing in some way, right? Because we're using eBPF, because we're directly in the kernel, we're seeing the event and we can actually allow this event to process or not. We're not looking at it from the outside. So this allows preventive security and on the system, on the network, on the file system, on the application, and synchronous enforcement. When there's a call happening in the kernel, we can say, stop. I want this call to be allowed or not. And it's going to be processed or not. There's different integrations that exist. Currently, we mainly use Kubernetes CRD and JSON to configure this with the tracing policy CRD I showed you earlier. In the future, we actually think of adding OPA. I think it's still in the work. So just what was presented before. So this idea is having more logic, using Rego typically to specify logic and correlation between different events to decide when to block a process depending on different criteria. Or even convert existing rule sets. We have customers that use Falco, for example, or pod security policies. So Falco uses Rego as well. And so we could translate this into Tetragon logic. So again, we can plug anywhere on the namespaces, on file access, on syscall, and so on, and decide to block calls in the kernel. So this is what it looks like without Tetragon, actually. If you have a system that is running in user space, and you actually detect malicious activity, but by the time the detection reaches your rule engine and you decide to act back to block it, it's too late. It's already been executed on the machine. So you're blocking something, but in between, the malicious activity might have continued. It might actually have triggered something else, another escalation that you will detect later on, or not. So by using eBPF, what we can do is that we're actually watching for syscalls or for events in the kernel, and whenever those events happen, we can say, no, stop it, kill the process before it gets even executed. So here's an example here where we have a user accessing etc shadow, reading it, and then we say, no, we don't want this user to write. So we see the event happening, and we're killing the process right away. Nothing else can be done. We can even prevent the reading from happening, so the reading and the writing won't happen. Right? So here, the example actually don't match. This is authorized keys, and this is etc shadow, but it will look the same, actually. Just to see if you're following. Here's an example with a remounting of root file system. So using the pivot root, which is the remounting, which is a very common vector attack. So here we can prevent this with this kind of tracing policy. We can say if a process is trying to remount the root file system, kill this process, and obviously alert us as well. We can get the log plus the killing, obviously. Here's an example where we actually see the capabilities, and these capabilities are fine, but they actually allow to write to etc password. So long as it's not being used for this is fine, but as soon as we detect that it's being used for this, we can kill it. And this could happen as well if capabilities are abused to change namespaces. For example, in a container, we could detect this and kill the container. So this is just a summary of what that is. Again, Tetragon allows for security observability, so we can see everything happening on the machine. And runtime enforcement, we can actually take action when it happens, right when it happens, and prevent the action itself. And again, we can export to pretty much anything that will support a JSON export and do correlation there. So Tetragon is an open source product that is part of the Cilium family. You can just download it, use it however you want. It allows for visibility. Yeah, I'm almost done. For process and syscall visibility, you can get L3 to L4 network visibility, so IP and TCP UDP typically. File access monitoring, you can see files being open for reading or for writing. Capabilities and namespacing when it comes to C groups, for example. And enforcement, you can enforce based on K-probes and trace points. We have some specific features that are only available in Tetragon Enterprise, which comes with Isovalent Cilium Enterprise. And this is extended network visibility, including the parsing of DNS, HTTP, HTTPS, and TLS. So this is in the enterprise version. CM integration, process ancestry information. So the interface I was showing you before that shows the process ancestry and the link with the with the different flows. High performance parsers, especially for DNS, HTTP, and so on. And file integrity monitoring, which is different from file access monitoring, in that with file access monitoring, you can see a file being opened or a file being written, but fortunately or unfortunately, I don't know, there's different ways to read and write a file in the kernel. There's different syscalls that have pretty much the same result with small differences. So if you were to do it yourself, you'd have to watch all these syscalls with the or pretty much. If this happens, or this happens, or this happens, I want to be told. We have an abstraction in the enterprise version that we call file integrity monitoring that takes all this in consideration, plus takes in consideration the checksum of the files. So it makes it much easier to check for integrity and for access to files. Plus advanced enforcement capability, threat detection, and baseline policies that are provided. So if you want to learn more, there's some books. There's actually 2 books, Security Observability with eBPF, that talks about Tetragon, that is available on this table, and I have more. If there's no more, just tell me. And there's another book that is there as well about eBPF in general. We have some labs, and there's actually a lab about Tetragon, open source, and showing how to block an attack. And there's a lab about security visibility in the Isovalent Cilium enterprise version with the nice interface I showed you before. These labs are accessible for free. There's just some marketing forms that you have to fill. And finally, we'll be present at different summits. You can come and visit us. There'll be the eBPF summit with a watch party here on the 28th of September. We'll be present at AWS Cloud Day in Zurich as well on the 29th, so just the day after. And then in Hamburg and in Munich for Container Days and Kubernetes Community Days. So thank you. I don't know if I have time for a few questions.
Yes, absolutely.
Oh, yes, great. Amazing.
Almost 10 minutes for questions.
Oh, my goodness.
Just repeat the question. Did you get one?
Hi, with the TLS visibility, can you do more than SNI, and if so, how?
No. Well, sorry. With the TLS visibility, can we do more than SNI? That's a good question. I'd be tempted to say no. I would check with engineering if they were here, but nobody's in the office at the moment. Well, so long as you don't actually get inside the encrypted stream, the only thing you can see is SNI, right? Plus the metadata around TLS. I would say we might be able to get more depending on where the TLS flow is coming from. And if it's been dynamically encrypted using KTLS, for example, and in the case of pod-to-pod communication with KTLS, then we might be able to see more and actually parse what's happening in there. But that's my answer, and I would check with engineering to be sure.
We have time. More questions? Some comments?
These examples, you were very eager to kill everything. Can you also just deny specific action?
That's a good question. The only examples I've seen so far is kill, but I know that we can also, and I don't know the specification for it, just reply with a fake answer pretty much. That would be another possibility. So pretty much replace the reply, right, instead of killing the process. But that would only work for some kind of syscalls, and other syscalls you would just have to kill. But indeed, I would say, like personally, I would say indeed, if possible, in the case of some attacks, it might be better to just return fake information or no information than to kill the process, which might be a hint for the attacker. But you know, I don't have an example at hand of something else than say kill.
Somebody else?
Could you rewrite specific requests? So, for example, I have elevated access rights, try to access something that I can turn it down, say, okay, good, I do the call, but with the corrected rights. So it's not pseudo execution, but only a user.
So could you catch an execution and replace it with something that you'd be okay with?
Yes. So not stop, not fake it, but it's like a container.
I don't know about this. I don't know if you'd want to do this because, I mean, if it's your own application doing it, then you should fix your application probably. And if it's an attacker doing it, I don't know why you would want to replay what the attacker is doing with other rights. You know, I mean, you might as well just prevent the attacker from doing it altogether. I don't know. But I mean, it's a good question, but I'm not sure. I'm not sure of the use case for this specifically.
The attacker believes he's sudo, and all he gets ever is non-sudo.
Yeah.
So it's kind of brain fuck.
Yeah. Okay, just make the attacker crazy. Yeah.
You said something about, there was an example about gRPC. Does that mean like there's a gRPC or I guess a protobuf parser within, like written in eBPF-C?
As far as I know, it is possible. We have different parsers available for eBPF. I don't know if this is what is used in this case for observability. It might actually be extracted for parsing. I would have to check. I don't know details on this.
Does anything ever get kicked back into user space as part of handling a probe that's set up in the kernel? So if there's like a user space component that you guys have, can it go, okay, I'm not really sure about this, jump back out, ask that, and come back in? I think no, but I just wanted to ask.
So yeah, I would think maybe some parsing might be in this situation. I would have to check which ones. But generally, the idea is to stay as close as possible to the syscall, and especially for policy enforcement, if you go out of the kernel, by the time you're out, you're too late to intervene. So we want to stay as close as possible. For anything that is taking action, it should happen in the eBPF program ideally. Yeah.
So if you use Tetragon, is there like still a use to continue using SC Linux, or would you just say put it in permissive mode and just run Tetragon? Or are they sort of...
Well, at this point, there's probably far many more rules written for SC Linux out of the box in your favorite distribution, which might be Red Hat, otherwise you wouldn't ask, than we have for Tetragon. Eventually, a lot of the logic for security and observability in the kernel might be replaced with eBPF. And not just from us. A lot of vendors are going into eBPF because it's just much more versatile. You can have much more logic without the addition of modules. So I would say, and this is from me, right, that potentially a lot of the logic from AppHome or SC Linux might get ported to eBPF along the way. At the moment, what you get from SC Linux is that all this logic comes with the packages in your distribution, and we don't have this yet. Right.
You mentioned before that you want to stay close to the kernel, but you also mentioned possible OPA integration. Wouldn't you have to connect to OPA during the calls for eBPF?
So the way I understand it, and this is not implemented yet, the way I understand it is that OPA would probably be used to generate eBPF programs, to generate the logic, right? eBPF programs can get quite complex. They're quite limited, but you can, link them to each other using the events and the structures. And so my understanding would be that you would write, as a user, you would write the OPA logic, and then this OPA logic would have to be translated into eBPF programs that would be independent from user space. Again, that's my understanding. I'd have to check with engineering.
One more question. So something needs to load all of these eBPF programs, right? How do you prevent an attacker from maybe unloading eBPF programs or maybe manipulating these programs? Because especially if you have like open rules that generate eBPF programs, these would have to be able to be like updated with policies, right? So
that's right. So injecting eBPF programs in the kernel is an administrator kind of task. You need specific rights to do it. And usually, I don't know about Tetragon. I would have to check about this. I know that in Cilium, what we do, because we manipulate eBPF programs as well, is we typically disable the possibility for non-admin users to manipulate these programs. But indeed, I mean, at some point, if you get administrator access to a machine, right, you can disable kprobs, you can disable eBPF, you can unload programs and so on, right? So the goal is really to prevent users from getting to the point where they can actually act on the kernel themselves, right? Thank you.
Okay, we are ready to start. So, yeah. Hi, everyone, and thank you for joining us on this session on simplifying Kubernetes autoscaling with Karpenter. So, my name is Simone Pomata. I'm a solution architect at AWS, Amazon Web Services. And today I'm here with my colleague, Scott Gerring. He's also a solution architect. We're both based in Zurich, and yeah, happy to deliver this presentation today. So let's see what we have on the agenda. So yeah, the topics for today are the following. So we start with an introduction about the traditional autoscaling model on Kubernetes. That includes pod autoscaling, node autoscaling, and what are the benefits and also some drawbacks of this approach. And then we go into groupless autoscaling, which is the main topic for today. And this is basically a new approach to autoscaling that has been created to address some of the drawbacks of the traditional autoscaling model. We will see how groupless autoscaling is able to launch capacity, to schedule pods on this capacity, the algorithms that it's using, and also how nodes termination is handled. We will do this in 15 minutes, then we have a 20 minutes demo, and then 5 minutes of Q&A, assuming we can respect all the times. Yeah, let's start. So let's start talking about traditional node autoscaling. So before I start, how many of you have used the cluster autoscaling in Kubernetes? Okay, so not a lot, so I will start from the basics. Basically in Kubernetes we have pods, of course, and where do those pods come from? So they can come from jobs, from deployment, from cron jobs, or from existing deployments that scale. And they can scale with horizontal pod autoscaling, with event-driven autoscaling, and other tools. So this is really basic. And what about nodes? Nodes actually are basically the machines where pods run, and they can be provisioned in different ways. So we have the manual provisioning, but usually in cloud providers you have cluster autoscaler, which is a way to automatically adjust the number of nodes in the cluster based on the resources requested by the pods. The cluster autoscaler is the most common approach, I would say. It has some drawbacks, by the way. We will see later which ones. And that's why there are also other solutions coming on the market. For example, Zalando did a fork of cluster autoscaler that became quite popular to address some of those issues. And some of those, let's say, changes have been pushed back in the upstream. There were also other attempts to try to solve a bit the limitations of the cluster autoscaler. They are not very popular at the moment. One of them is also deprecated. But yeah, that's a bit what the market looks like at the moment. Well, before we go a bit deeper, what are the benefits of a cluster autoscaler? So with a cluster autoscaler, you can automatically grow the cluster to meet, in fact, the demand of resources. You can reduce the cost of infrastructure because you don't need to provision a certain number of machines that are always fixed, but you can downscale or upscale them automatically based on the traffic, based on how much resources are requested. It's vendor neutral, so the cluster autoscaler is a component that supports different cloud providers, basically all of them. It's widely adopted. It's the most common approach. And it works great. It's been tested for up to 1,000 nodes, so cluster with up to 1,000 nodes. The way it works is the following. So whenever you have pods that are, this works. So whenever you have pods that cannot be scheduled because there are no resources in the cluster, those pods become pending. And when the pods are pending, what happens is that the cluster autoscaler kicks in, looks at let's say, the resources that are needed by those pods, and launches nodes to schedule those pods on. Now, the nodes are launched out of a pool that you have to pre-provision. And this pool is called a node group. In case of a Kubernetes cluster on AWS, this node group is basically an AWS autoscaling group, which is a, let's say, autoscaling set of EC2 instances of virtual machines. So this is how it works. You have these node groups in your cluster. You define minimum, maximum size, and then the cluster autoscaler will automatically change the number of instances in this node group. So this way of scaling from the cluster autoscaling is called node-based autoscaling. And there are also a few drawbacks and caveats to keep in mind from this approach. So one of the things to keep in mind is that one node group is to be deployed in one zone, in one availability zone, and should only have ideally one instance type. So it should be coherent, it should be consistent in terms of availability zone, instance type, and also labels. So if you need, and you should usually use multiple availability zones, sometimes also multiple instance types, then you will have many node groups to pre-configure, to pre-provision. So let's say 3 availability zones, 4 instance types, it's already 12 node groups. Also, in case there are any errors on provisioning a new node, the error handling is timeout based, because the cluster autoscaling is not aware of what is going on in the cloud provider. So it can slow things down in case the node fails to launch. It's tested up to 1,000 nodes and 30 pods per node, so it may be a limitation for very large clusters or very dense nodes. And yeah, those I would say are the main things to keep in mind. And what we have been thinking at AWS, and also what the community have been asking for, is there a way to simplify the node provision, the autoscaling? Is there a way to make it easier without having to, let's say, pre-provision all those node groups? And is there also a way to make it faster on large clusters or at scale? So those are the main questions. And in order to, let's say, satisfy those questions, the approach that we have been looking for is the following. So what if we, really remove the node groups and we go groupless, basically? So the idea here is that if you are groupless, you can provision capacity directly. So whenever pods need resources, you provision nodes without having to pre-provision node groups. Basically, with this approach, instead of pre-provisioning certain instances with specific CPU or memory or GPU, whatever, you look at what the pods are looking for. So what resources the pods are asking for, and then you choose the best instance out of all the possible instances in the cloud provider. So it's less work, more flexible. Basically you generate nodes out of pods instead of looking for the nodes pre-provisioned and then choosing one of them. And this reduces the, configuration burden, because you don't have to, let's say, pre-provision those nodes in advance, to pre-provision the node types, the node groups in advance. This reduces the complexity a lot, because you don't have, as I already mentioned, all those node groups to configure. And based on these, let's say, based on those considerations, we have come up with a service that is called Karpenter, with a functionality that is called Karpenter. And Karpenter is basically a groupless node autoscaling mechanism that you can use in Kubernetes. The way it works is the following. So whenever you have some pending pods, so pods that cannot be scheduled because of missing resources, Karpenter will look for the requests of those pods. So the resources requested by those pods will look also at the constraints of those pods, and then will automatically compute the right node type, the right virtual machine type to use for those nodes, launch the node for those pods, launch the node, and then schedule the pods right away on the node. And then over time, if you enable consolidation, which is the step here, Karpenter will also look at existing nodes with existing pods running on them, and will try to find ways to make them more efficient. For example, if one node is running let's say, pods requesting 2 CPUs, but the node has 4 CPUs, Karpenter will automatically replace that with a node with 2 CPUs instead. So it will automatically adjust the number and the type of nodes. Yeah, and the way it works is that behind the scenes, in case of an AWS implementations, we use the EC2 create fleet API, so an API to request instances. So what we do, what the Karpenter service does is it looks at the resources requested by the pods. It makes a list of all the potential instances that can run those pods, and then passes that list to the EC2 API. And the EC2 API will automatically pick the cheapest instance out of those. So in this way, costs are always optimized. The Karpenter's service is able to look at different, let's say, take into consideration different APIs and different parameters of pods. So it can look at resource requests, first of all, so how much CPU memory, which GPU the pods are requesting. It look at node selectors and node affinity, spread constraints, and so on. And it will keep all those things into consideration when launching nodes for those pods. It will also work with the well-known Kubernetes labels. So if one of your pods requires, for example, ARM64 architecture, it will work well for that. So it will only choose nodes that have that kind of architecture. Or if you request the pod to be in a specific zone or on a specific instance type, this will also be taken into consideration, of course. So I mentioned before that Karpenter tries to be cost optimized. That's one of the goals. So the way it works, so the algorithms that Karpenter uses to be cost optimized is the beam packing algorithm. So the way it works is that let's assume there are 10 pods that are pending. Those pods are ordered by resource consumptions in a descending way. And then the biggest pod is taken into consideration, and the smallest node for the biggest pod is provisioned. And then the biggest pod is scheduled on that node, and also smaller and smaller pods will try to go on that node. After that, the second biggest pod is taken, and another node is launched with that mechanism, and so on. And this is one of the most efficient, one of the most cost-efficient algorithms for scheduling pods on nodes. There's definitely room for innovation, so there's no, let's say, a fully efficient algorithm in that sense. So we are always open to change, to improve the algorithm being used here. And what I just mentioned is how the nodes provisioning works. Now, what happens when you have nodes already running and you want to stop them? Maybe because they are empty or because they are not efficient anymore. So Karpenter also handles the termination. And there are different reasons why Karpenter may terminate nodes. So the first one is when a node is empty. All the pods has been descheduled, and then the node is empty, so the node will be shut down by Karpenter. You can define a shutdown grace period, so a period of time before the node is shut down, for example, 30 seconds, 1 hour, whatever. Nodes are also shut down if you use spot instances when there is a spot instance activity. Spot instances are basically instances in our data centers that are not used by other customers. And if you choose to use them, you get exactly the same compute capacity as with the regular on-demand instances, but you pay up to 90% less, with a drawback that at any time we may require that capacity back. So in that case, when a capacity is required back by AWS, the node will be terminated by Karpenter, and then another node will be started for moving your pods on that. And nodes are also stopped in case of consolidations. So it's the last line here. Consolidation is an optional feature that you can enable. And consolidation will always look, so we look at every node on an interval. And whenever each of those nodes is not running the pods in an efficient way, meaning that there is a smaller node that can be used, or maybe the pods can be distributed on other nodes in the cluster. In that case, Karpenter will automatically stop that node and either redistribute the pods on the other nodes or launch another smaller, cheaper node if needed.
Consolidation, does it still look only on the requests, or is it able to also look at the actual usage?
It will look at the request. So it's all based on the request. Great, so that's basically it for regarding the slides. The project is available here at this link on GitHub. It's open source. It's, of course, let's say, initially developed by AWS, but it's vendor neutral. And the aim is to support over time more and more providers. And the roadmap is publicly available, so you can check it there. And now it's time for the demo.
Cool. I'll walk around the back and take
Yes.
Is that legible roughly? Cool. This is the hardest part, I think. Oh no, there we go. Cool. Hi everyone, I'm Scott. As Simone mentioned, I've got a bit of a demo. Is anyone or everyone vaguely familiar with K9s, this little Kubernetes client that I'm going to play with just here? Raise your hands if you're not, it's probably better. Cool. So it's basically what you can do with kube control. It's a bit more graphical. I'll click around through some different CRDs just to kind of show what's going on in the cluster. I'll try and explain it as I go because it's, if you haven't seen it before, it's probably a bit confronting. So I have one window here with that in, and I have a text editor here. I'll kind of jump back and forward to explain things. So what we've got to start with is this little kube cluster that I've got running in my AWS account. It has very little running on it at the moment. It has some Fargate pods. This is our serverless container orchestrator. So basically, you want to run some containers, but you don't want to bring any servers to the game. And what I've used that for is to run the core stuff you need to run a EKS cluster, essentially. So we've got core DNS, and we also have Karpenter. My goal here is to only use Karpenter to provision the rest of the capacity. So I've used Fargate because it means I don't have to have servers to get the cluster up, and then after that, I'll use Karpenter on top of that. What we've also got is a bunch of deployments that place different fun demands on the cluster. So you can kind of guess what they're for. There's one that inflates it. There's one that inflates it with ARM, so ARM64 architectures, and there's one that needs some GPUs. So none of them are scaled out at the moment. There's no capacity in the cluster. And I'll kind of show you how that'll work first in terms of configuring Karpenter, and then try and make this create some nodes, hopefully quickly enough that it seems impressive. We'll see. So you configure Karpenter with a CRD like everything else in the land of Kubernetes. You have a provisioner, essentially. You can have one provisioner, or you can have multiple provisioners. Part of the love of Karpenter, I suppose, is that you can simplify a lot of this node configuration, which is what Simone was mentioning. So it's cool if you start with kind of the least amount of configuration as possible rather than going crazy breaking it down. So I've got one simple one here, and I'll kind of explain the stuff that it does. This starting one, TTL seconds until expired, it controls how long a node can possibly live for in total. So if you set this to something other than infinity, nodes have a fixed lifetime, which is nice because over time you have this natural attrition and nodes are replaced with new nodes with newer versions of the operating system and the base AMIs, which kind of gives you a decent or a slightly improved security posture off the bat. This one here is saying how long after a node is emptied of non-daemon pod sets should the node be killed. So 30 seconds is quite aggressive. You could imagine that you might push that out a bit more if you weren't trying to do a demo, so that you have a chance of things being scheduled back onto the node before it's knocked on the head. The interesting part here is the requirement. So this is kind of narrowing down the set of instances that it's considering when it provisions nodes. In some cases, it's a I haven't explained that very well. In some cases, it's a narrowing. So here with the instance types, I've got nothing specified. It's fully commented out. So Karpenter will configure or consider anything that possibly exists in Ireland where I'm running it in all of the availability zones. You can imagine that some customers come in and they have a bunch of savings plans or some pre-commitment to certain capacity, and here you could narrow that down so you have this nice transition where you're still using instances that you've proof-committed to, basically. But the way I've got it now, it'll just use anything it can find that satisfy the pod demands. These ones are a bit different. So by default, the capacity type is on demand, so it won't use these interruptible instances that Simone mentioned before. If you put on spot and demand, it'll try and use as much spot as it can, and it will try and select spot instances so that they match the requirements of the outstanding pods, but they're the cheap or the least likely to be interrupted. If you use on demand, it'll just try and use the cheapest because there's no risk of interruption. So with spot, it's a bit of a different strategy. And down here, we're saying basically, let's use ARM as well, because by default, lots of workloads in Kubernetes don't have the architecture tag on them. So if you just start throwing in ARM instances, heaps of things won't work. In this case, I've annotated everything nicely, so I'm happy for it to use both. And the other thing that's worth mentioning is that it works with taints and toleration. So if you have an existing cluster where you're using cluster autoscaler and you kind of like the sound of this, but you don't want to big bang everything across, you can introduce Karpenter and you can use taints to ensure that it only schedules a subset of the workloads, essentially. So like a particular subdomain or what have you in the business. So we'll jump back over here and I will launch a couple of pods of this ARM deployment and we can see what happens. And sort of straight off the bat, you would expect that it can't schedule anything. We have no nodes that it can run on. You can see we have 2 pending pods. And if we describe them, you can see it's saying it can't schedule them. The 3 nodes that are available are Fargate. Fargate only ever runs 1 pod at once, so you can't place more things onto it. So it's decided that it should launch another node. If we go and have a look, we can see this node's been coming up for 21 seconds, and we can have a look at what it's picked. So straight away, we can see the instance family is C6G, which I can tell you is a Graviton instance, so it's picked one of our ARM chips because the pod requires ARM. It's using spot capacity, so it's interruptible, but it's cheap. And it's fairly small. It's a 4XL, so it doesn't have a great deal of vCPU assigned to it. So it seems like a sensible decision, really. We've asked for a small ARM machine, and we've got a small ARM machine. If we give it a second, it's already come up, basically. So it's already running kubesystem, kubeproxy, and now it's running these other pods that I asked for, which is quite impressive, I think, in comparison to autoscaler. We've gone from having unschedulable pods to a new machine with the pods running on them in just 58 seconds, I think. So it failed scheduling 70 seconds ago, and it started 12 seconds ago. If we jump back over here and have a look at that, we can see kind of how we've asked for that particular set of pods. And it's pretty normal. There's no surprises. We've said, node selector, I need ARM64. The containers pause. It's not very exciting. It's not doing anything. But it's basically using 1 CPU, and it needs to run an ARM. We've got an ARM instance with 2 vCPUs, or 4, I think. It's done pretty much what we expect. Bear with me. So then if we jump back, we can see these other ones. So this inflate one is pretty generic. It says that it can run on ARM or it can run on x86. So if we schedule it, we can see it's immediately running. And if we go and have a look, it's decided to run on this ARM instance, which is pretty cool. So we've said that it can run on any. It's seen there's an available ARM instance. It can run there. It's scheduled it there. Whoop. If we jump back out and chuck another instance on, it should schedule that on the same node, unless we're out of, no, we're good. But there's another interesting property on this one, which I will show you quickly. So this is the YAML for the pod we just ran. We're basically saying what I just mentioned. It can run on ARM or AMD 64. But we also have this topology spread constraint. So we're being good cloud users, and we're saying, hey, it would be nice if we can spread instances of this across multiple availability zones. I've said max skew 2, which means the most it can be wrong is 2 pods. We've got 2 pods in one AZ at the moment, so we're good. But when I schedule the 3rd pod, it should have to create another node. And if I have prepared a good demo, we will see that happen. Can't schedule it. It's pending. And we can see the Fargate ones didn't work, and we have a topology spread constraint violation on our Graviton node. So it's going to launch another node, which is exactly what we want here. And we can go see what it's launching as well. So if we look at the previous one where our existing capacity is running, we can see it's running in EU West 1B. This one should be running somewhere else. And it's running in EU West 1C. Also interesting here is that the previous pods are running on Graviton, so ARM64. This new one, it's picked the cheapest thing it could find, or the least interruptible cheap thing because it's on Spot, and it's picked a T3, which is an x86 machine. So we've now got this one deployment spread across 2 different architectures, and in this case, it's had to launch a new one because of the availability zone requirement, and it's picked a very small x86 machine. And if we're lucky, it's already come up as well. It's launching the pods, again, fairly quickly. And the last one we have here is this GPU one. So I'll quickly start it doing something. We'll see that it can't schedule, and we'll see that it can't schedule because nothing has NVIDIA.com GPU. If we jump over here and have a look at the YAML for it, we've basically got the architecture constraint, AMD 64. I don't think we have any Graviton machines with NVIDIA GPUs in them, so this is probably a bit redundant. And it's saying that it needs something with 1 GPU, which none of our existing nodes can satisfy. There's none that have a graphics card attached, which is good. If you launch things that don't need a graphics card, it's nice if you don't pay for a graphics card. So if we jump back to our nodes here, we can see this new one coming up. We can have a look at it. We can see it's a G3S extra large, so it's an older, cheaper one with an NVIDIA graphics card. It's not too big. It's using Spot for it. Ultimately, it's done what we expect. These take a bit longer to launch because it's an older instance class, but it'll come up pretty quickly. So then the opposite way around. What happens if we scale down? So if we remove all of the capacity of this one and this other one, we would expect that we end up with a couple less nodes, essentially, because we've removed all of the demand for the ARM one, and we've removed all of the demand for the small x86 one. So we can go have a look, and we'll have to be pretty quick because we have 30 seconds timeout. And you can see that we have this emptiness timestamp put on. So Karpenter's immediately whacked a label on the node saying this thing has been empty since 16:27 and 2 seconds, and by the time I push escape, it's probably almost gone. Ah, there they go. So it's got rid of them already. I've got this 30-second timeout to get rid of the nodes again. It's very aggressive for most normal workloads, but you can see that it responds quite quickly to demands for capacity and then pulls it all back in again really quickly too. If we jump on this one now, we can see that it's got the NVIDIA device plugin, unsurprisingly, because we've asked for GPU capacity, and we have our inflate GPU running. If we go back here and we say, cool, I would like one instance of a regular x86 pod, we would expect that to probably be scheduled on the GPU node as well. Not super cost effective maybe in lots of cases, but we have the capacity for it. And it has. So for my own sake, so I don't have to remember to turn this off all again tomorrow, I will go and scale everything back in. My nodes will all be killed, and I'll have a nice empty cluster and 10 minutes to spare. Cool. Thank you. Something that Amazon people do, because we are slightly masochistic, I suppose, is ask everyone for feedback as well. So if anyone has time and passion, and seeing as we've given you 10 minutes to ask us questions if they're interested, you can also tell us if it's an interesting topic.
I don't know if there are any questions. Simone and Scott can answer them right away, so please keep your mic.
And you can
We
lean
have
in.
time. And the pizza is coming, so good news.
Hey.
Right?
Yes, so the question is with the cluster autoscaler, you have the possibility to balance between node groups so that you don't have like everything in availability so one like that. How does that work with Karpenter?
So you would use the...
In the morning, somebody starts a deployment, then the next one starts a deployment, and I don't want to have all nodes in one availability.
So you would use the topology spread constraints on the deployments themselves. So you would encourage people who have this availability requirement to say, okay, this deployment, this set of pods, they should be deployed spread across as many AZs as possible. Because there's also sometimes the counter argument. You see with some big customers, they have workloads that are really chatty, and then you start paying this cross-AZ costs. So it's nice if you don't just force everything to spread out by default, but rather give the people who are building the individual workloads the option to say it. And you could also use the policy engine to enforce it if it was a requirement. Trying to tie it all together here. Does anyone run large EKS clusters and think that this is something cool, or is it not so common? One person at least.
I was wondering about the max SKU parameter that you showed before. Was it a max number of this type of pod per node or per availability zone?
The max CPU in the provisioner is the maximum size that provisioner will ever create in terms of total consumption. So if you create one machine for the provisioner with 1,000 vCPU somehow, it'll stop. Or if you create 10 with 100 each, it'll stop and it won't.
The max SKU.
Oh, the max SKU, sorry, I misheard.
Sorry.
What was the question?
So, yeah, so the max SKU,
yep.
You had set it to 2.
Yep.
So it started that machine in a new availability zone.
Mm-hmm.
Was it because it was 2 pods maximum per node or per availability zone?
It's how many pods it can be away from ideally balanced, as I understand it. So when you have 1 pod, it's ideally balanced. When you have 2, it's 1 pod, not ideally balanced. And then when you add a third, it has to add another one, because then you would have more than 2 pods out of balance, as I understand it.
Like typically in EUS1, it will get back to
yep.
zone 8.
Yeah.
And you can also define the label, either zone or node,
okay.
for the split topology.
And if you can also limit it to a subset of AZs. So you can say in the provisioner, you only use A and B in US East, for instance. If you use all of them, it'll rotate through all of them. The balance will be over the total set of AZs you've made available to it.
My experience with EKS groups is that it takes about 10 minutes for you to spin your nodes up. How is it so quickly? Is that a single EC2 instance with bottle rocket, or what is it?
They are AWS employees. High priority.
Yeah, one of the reasons is the fact that the autoscaling group is introducing some overhead.
Yep, yeah. Sorry, we can hand this back and forward.
Thank you. Yeah, one of the reasons is that the autoscaling group introduces some overhead because it has to calculate the right instance, do some reconciliation. Usually this is 30 seconds. And then the rest of the time, it's the time it takes for the instance to come up, to join the cluster and so on. I think those were Amazon Linux, no? Or
AMIs with the EKS space in it.
Yes,
like
yes,
yes.
Yeah, it's the optimized, but it's the same you have also in the regular cluster autoscaler. The difference in speed is due to the different mechanism that the nodes are started.
We also say that for this, between a pod being unschedulable and a node being provisioned is less than a second, usually. So Karpenter sees it and it immediately makes a call to the Fleet API to provision capacity. And there's this big lag with the auto-scaling group where you ask it nicely and it thinks for a while and eventually capacity results. But yeah, it's quite fast. It's also competitive with Fargate, which is interesting.
Also, yeah. I mean, one of the reasons that we developed, I didn't mention that a lot during the presentations, but one of the reasons is the simplicity, because you don't have to pre-provision those node groups. And another reason is the speed, because as you mentioned, it's really fast. Yeah.
So that makes the use case with the priority classes obsolete that you currently have, where you have this high priority class and free up the pods so that they can run and then wait for the node to come up and then schedule the ones with the lower priority class? Or is that still a thing and possible to use?
Yeah, maybe I can start and then I leave it to you. Well, one of the reasons for that could be to have capacity pre-provisioned in case you want to be sure to have that capacity. In terms of speed, you have seen the speed. So it's really depending on the workload, but for most workloads, the speed of nodes coming up is quite acceptable, I would say, with this Karpenter approach.
No, that's
Okay.
Can I convince Karpenter to change the base image over time, so that I move from on-the-spot images to normally started images to you can pre-order some computing time, so it gets even cheaper over time if my base load just rises.
So I'm not sure if I unpacked that properly. With the reserve capacity, so you prepay however many dollars per hour for compute, that's what you're alluding to, I think?
Not really. There are different image types. So I can pre-order computation time. So I have a fixed amount which I pay, but I have to. They are not easily startable and stoppable like the rest. So can I convert over time? If I see I have 200 on-the-spot nodes and 50 are always used, so I can convert them into the more static types?
Not sure I fully understand, but maybe Simone does. Sorry.
Maybe the question is if you. Yeah, thank you. Maybe the question is if you can enforce something like a ratio between spot instances and on-demand instances and maybe reserved instances and change it over time. Is that the question? Yeah, I mean, in that case, yes, you can. We also have a use case in our documentation about enforcing, you enforce that in the provisioner. In the provisioner, you can say, not directly, but by using other mechanisms, you can say the percentage of instances that should be spot and the percentage that should be on demand. I think it's also done with the topology, with the spread topology.
Yeah,
so
you do something funny with labels to force it to spread it out. It's not a direct property where you can say, 60% spot, 40% on demand, for instance, but there's a coarse mechanism using for labeling to do it.
Exactly, yeah. And also you mentioned the case when you can reserve capacity and have it, let's say, dedicated to you. In that case, we saw that we have two different types of paying model, on demand and spot. Spot is the one that is interruptible, on demand is the one that is not interruptible. If you acquire any reservation, 1 year or 3 years commitment, whatever, it will apply automatically to the spot, to the on demand. Yeah. Good.
Thank you, everyone.
Thank you so much.
Thank you.
So pizza is coming in 7 to 10 minutes. We'll bring down some beers and soft drinks, and we use this table for the pizza.
Yes, we're going to get rid of everything. No problem.
Yeah.
Thank you so much for watching. See you. Bye bye.